Welcome everyone. I am Pablo Macmillan from CSE. My topic is Applications of Mathematics in Rockets and Satellites. Introduction. Early British involvement with satellites considered mainly of tracking those launched by other countries. But in October 1971, Britain successfully launched its own satellite when the Black Arrow rocket took to the 6 over Woomera, South Australia, and placed Prospera in low Earth orbit, far from making the start of extensive British involvement in space launch vehicles. Black Arrow, which built on the earlier Blue Steel missile and Black Knight rocket, was the end point of independent British headquarters, and the program was cancelled. From then on, British involvement in space concentrated mainly on satellite design and collaborative ventures, particularly as part of the European Space Agency. An expansion to this was the Hotel project carried out by Rolls-Royce and British Aerospace during the 1918s, but this did not get beyond the design phase. British scientists and engineers have also been active in designing instruments that have been carried by satellites to observe the Earth or explore the solar system. Mathematical aspects of NASA missions. Teachers of mathematics, like model most adults in today's world, can hardly fail to be aware of the rapid development of space science. We realize that the spectacular achievements of the space program have depended heavily on mathematics. Mathematics that is generally complex, advantages, and well beyond the level of most secondary school curricula. Even, even though this pre- preference is valid, there are many significant aspects of space science that can be understood using only high school mathematics. The exploration of space naturally uses the tools and techniques of astronomy. In turn, in gaining much new information as a result of sending specific probes and satellites beyond Earth's atmosphere. Because astronomy has simulated the growth of many of the concepts and methods of mathematics, the high school teacher will find here much that is familiar. However, in some instances, the way mathematics is used to solve real life problems in rather different from methods emphasized in school courses. In this opening chapter, we shall examine several recent achievements of the National Aeronautics and Space Administration and identify mathematical ideas and questions that may be of interest to high school teachers and students. When appropriate, we will refer to problem illustrating some aspect of the subject and working elsewhere in the book. The Space Shuttle. The Space Shuttle is a true aerospace vehicle, takes off like a rocket, uh, operates in orbit as a spacecraft, and lands like an airplane. Due to this takes a complex configuration of three main elements: the orbiter, a delta weakened spacecraft aircraft about the length of a twin jet commercial airliner, but much bulkier, a dirigible like external tank, the only external element secured to the orbiter's belly and containing 2 million liters of propellant, a pair of reasonable solid rocket boosters, each longer and thicker than a railway tank car and attached to the sides of the external tank. Each space shuttle is meant to be just one element in a total transportation system linking Earth with space. In addition to providing for continued scientific investigations by transporting such systems as the Space Lab and the Large Space Telescope. Recently renamed the Edwin P. Couple Space Telescope into orbit, the space shuttles are also expected to carry the building blocks for large solar power space stations or hug antenna bearing structures for improved communication systems. Structures that would be too fragile to stand up under their own weight on Earth will be folded up the shuttle's cargo bay and assume their final shapes in the microgravity environment of space. The shuttle will also be capable of carrying a workforce of 7 people and returning them home after the completion of their work. The planetary promise. The launch of two Voyager spacecraft in the summer of 1977 climaxed a series fruitful missions of planetary exploration, including the Mariner, Viking, and Pioneer series of probes to Mercury, Venus, Mars, Jupiter, and Saturn. All these missions send back new information about the structure and composition of these planets and their associated moons. We focus in the book on the some of the results of Voyager 1 and Voyager 2. This props which benefits from more highly developed instrumentation and computer capability than their predecessors. Approach it closer to Jupiter and Saturn than previous flights did. Stunning pictures result showing the unanticipated presence of active volcanoes on Jupiter's moon and the fine structure of Saturn's rings. Among the mathematical problems that arose in these missions were the following: transmitting spacecraft observations back to Earth, determining the time of transmission of spacecraft observations, calculating the rotation period for planets such as Saturn, which is not solid and has no outstanding observable features like Jupiter's Great Red Spot. The mathematics of orbiting the Earth. But why does a rocket or satellite or space station need to be moving sideways so fast to stay in orbit? The answer is mainly geometry. As you know, the Earth roughly spherical. While it is possible to go around the Earth in an elliptical orbit, we are going to think about the simple case of a perfectly circular orbit. If you think about, you will see that a rocket going around the spherical Earth in a circular orbit some height above the ground will stay at the height above the ground the entire orbit. This is kind of obvious, but it really is the key to understanding the mathematics of being in orbit. The rocket equation. Now that we know what is meant to get a satellite into orbit, let's think about how we get in there. In other words, let's think about what determines how big a rocket needs to be to lift a satellite into space and get it moving sideways fast enough to orbit the Earth. Do being with, let's contemplate what we have to do to put a person or satellite into orbit. The answer is that we need to attach a rocket underneath this payload that has enough fuel and power to lift the required mass into orbit. But the rocket we just attached to the payload also some mass, which means we need other rocket under the first that has enough fuel and power to lift it. But the second rocket we just attached also has some mass, so we once again need another rocket to lift it and on and on and on Even if a rocket's payload is small, it needs a lot of fuel to lift it, and it needs fuel to lift the fuel, and so on. As I said earlier, space is only 100 km away, but it's 100 kilometers straight up, which makes it hard to get to. Space is only 100 km away, but it's 100 km straight up, which makes it hard to get to. There is an equation that summarizes this whole situation and tells us roughly how much fuel is needed to lift a given amount of mass into orbit by a particular rocket. It is called logically the rocket equation. We are not going to go into all the details of this equation, but the gist is that is tells engineers how to calculate the speed gained by a rocket as it burns its fuel. In particular, the equation says that the speed increase is proportional to the logarithm of the initial mass of rocket itself, the payload and all of its fuel, divided by the final mass of the rocket. This ultimately tells us that adding more and more fuel to a rocket observes diminishing returns in terms of speed gained since, as we've seen, all of that fuel requires even more fuel, which is exactly why rockets have to be such enormous, magnificent, and beautiful machines. Conclusion: humanity rockets more efficient, more su- su- sustainable, and much less costly access to space. If it wants to dramatically expand its use of Earth orbit and make interplanetary space part of its economical sphere, we need waves to get into orbit and to reach other planets that do not leave large amount of debris, require enormous amounts of propellant, or take incrementally long periods of time. The space together systems described in this book offer various solutions. Space elevators would provide an easy and regular way to get into Earth orbit, and electromagnetic momentum exchange diggers could send spacecraft from low orbits up to higher ones, and vice versa. Others could even orbit return capables or send spacecraft on their way to other planets. Further out into space, momentum exchange together or aerobraking together could, could be used to capture spacecraft into orbits around the Moon, Mars, and Jupiter. Artificial gravity provided by long spinning tethers can yes the life of astronauts during their interplanetary travels and counter unwanted physiological changes to ensure that people can live and work in orbits with too high levels of radiation. Electrostatic tethers that sweep away dangerous charged particles around the Earth or even Jupiter may be deployed. Togethers may one day become as invaluable to space travel as chemical rockets today. The 22nd century may see a fleet of spinning togethers strategically placed around Earth, the Moon, and Mars, creating efficient interplanetary highways for spacecraft that require almost no propellant. The tether applications with potentially the most dramatic impacts are complex and will need large scale, large and expensive development. The space elevator requires revolutionary new materials, and all large scale togethers will exhibit complex dynamics that need to be fully understood to ensure stability and control under all circumstances. Damage protection is an important usage, both in terms of tether materials and concepts, and in terms of collision and impact avoid us. There are serious risks associated with having a capable tens of kilometers long rotating in orbit together with other satellites. Thank you.